Alright, so in this video, now that we have our heat diffusion equation from the last part, we'll be able to actually apply it to a problem. So for this problem, we'll be using Python um, and explicit differentiation to kind of simulate the temperature change in a bar. So we've got the bar of all one solid material, and this is a unidirectional problem, so we'll be using that equation I derived just for the x direction in the last part of the video. And so initially, our bar is at 20 degrees Celsius. And then at time equals 0, we're going to heat the left side up to 50 degrees Celsius and hold it there, and heat the right side up to 80 degrees Celsius. And then we'll be able to use Python to kind of show how the temperature of this bar changes with time. So I'm just going to go ahead and rewrite the heat diffusion equation from the last part of the video. And now we can go ahead and apply it to our problem. So in this problem, there is no heat generation. So Q dot is going to be equal to 0. And then I'm going to go ahead and rearrange this a little bit. I'm going to divide rho Cp to the other side. And so we will have K over rho Cp times the second derivative of temperature with respect to x. And that is going to be equal to the derivative of temperature as it changes with time. And so we can rewrite this in terms of the thermal diffusivity coefficient, alpha. And now to solve this problem, we're going to create approximations for both of these derivatives. So I'm going to go ahead and start with the first derivative as temperature changes with x. And to approximate this, we're going to go ahead and divide the bar up into even increments. And so we have a bunch of different increments in the block. And I believe the length of the bar in this problem is 20 meters. And we'll have increments of delta x. And for this problem, we'll set delta x equal to 1 meter. So we can index these increments. I'm going to use j. We'll have 0 on the left side, all the way to j equals 20 on the right side. And so we can use known temperatures to kind of approximate this derivative. And so to do that, we'll use the temperature of the next block that we're at. So say if we're at a block somewhere in the middle here, we'll use the temperature of this block here, subtract it from the temperature of the block that we're at, and then divide it by the change, which is delta x. And so this gives us an approximation for this derivative and simplifies the problem a little bit. And so then we'll be able to use this same thing to approximate the second derivative. So this term here gives us the slope of this block. And if we subtract it from the slope of this block, that'll give us an estimate for the second derivative. And so to do that, it'll just be the temperature at j minus the temperature at j minus 1 over delta x, and then divide this by the change, which is just delta x. And so now I'm just going to simplify this with a common denominator. And so the common denominator will just be delta x squared. And so we'll have Tj plus 1 minus 2 Tj plus Tj minus 1. And so this is our approximate form for the second derivative. And then we can go ahead and do the same thing for the derivative of temperature with respect to time. And so to do this, we're going to need to set increments for the time. And I'm going to go ahead and call that n. And so our time will be equal to n times our delta t. And in this problem, we're not going to have a set delta t because I'll be manipulating it in Python to kind of show how it changes our simulation. So our approximation for the rate of change of t with respect to time is going to be, now we're not going to change the block that we're at, we're just going to change the time increment. So we'll have tj at time n plus 1 minus tj at time n. And all of these terms are at time n. And this, we just have to divide by our change, which is delta t. And so now we can go ahead and shove these into this equation here and start to get at the equation we need to code into Python. So we'll have alpha times our second derivative approximation. So we'll have delta x in the denominator, or delta x squared, times tj plus 1 at time n, minus 2 tj at time n, plus tj minus 1 at time n. And then we'll set this equal to our approximation for the derivative with respect to time, which will be tj at time n plus 1 minus tj at time n. And then I'm just going to go ahead and divide our delta t over to the other side. So this is our equation. Now I'm just going to manipulate it a little better because we'll be able to know these terms as well as this one, and we're really just looking for the temperature of the block at the next time. So I'm going to go ahead and call this constant term just r, because we'll know alpha, that'll be determined by the material of the bar, and then we have set delta x at 1, and then we'll be able to pick different values for delta t. So I'm going to go ahead and get myself a little bit more room. And I'm going to go ahead and distribute r out across the left side of the equation. So it'll be r times tj plus 1 at n minus 2r times tj n. We can move this term to the left side of the equation. So it'll be plus tj at n. And then again, distributing r, we'll have plus r tj minus 1 at n. And this is all equal to tj at n plus 1, which is what we're looking for. And then I can just go ahead and combine these like terms. And so this will become 1 minus 2r times tj at n plus r times tj minus 1 at n. And that's all equal to the temperature that we're looking for. So now we can go ahead into Python and plug this in, and we'll be able to kind of iterate through a loop and find all the temperatures across the bar. So now that we have the equation we need to kind of create the temperature profile as time changes with our bar, we can go ahead and code it into Python. So I've went ahead and imported NumPy as NP, and we'd like to graph these, graph the temperature profile. So I imported make subplots from Plotly. So how we're going to start is we're just going to go ahead and define our constants. So our alpha equals 1. Our dt is going to equal 0.5, and then dx is going to also be 1. And so then from here we can calculate r, which is alpha times dt divided by dx squared. And then we can go ahead and set up our initial temperatures. So our initial temperature before we start is 20 Celsius. And then our initial temperature on the left, once we start heating each side, is going to be 50 degrees Celsius. And then our temperature on the right is going to be 80 degrees Celsius. So now we want to create an array with our temperatures to kind of represent the increments in our bar. So we'll have 20 increments, and we will use the function npfull to create an array filled with our initial temperatures. So we'll have the shape be n, and we'll fill it up with our initial temperatures. So now if we look at t, it's all 20. And so then when we go ahead and kind of start our simulation, we want to set the first element to t left and the last element to t right. So now if I go ahead and run this, it's updated with 50 starting on the left and 80 starting on the very right of the bar. Now all we need to do is go ahead and implement our equation, which I have it pulled up right here, and then go ahead and graph it. So what we want to do is we really only want to work with the inner elements of the list. So just kind of these, because those are the only ones that are changing. So to do that, we can use numpy splicing. We want to start at the first element and grab the last. And so splicing never goes to the last element. And so this will only grab the inner portions of the bar. And so from here, we just have to set this equal to our equation. So we have r times our t values shifted 1 to the right. And so it'll be from 2 all the way to the end, plus 1 minus 2 times r times our t values at n. So that is just going to be indexing from 1 to -1. And then we have r times our t values shifted 1 to the left for j minus 1. So we'll just have from the beginning of the list to the second to last one. So now if we go ahead and look at t again, you can see that the temperatures are starting to change as the heat diffuses into the bar. And so we want to loop this over and over again so we can run it for longer times. And so I just have to stick this into a for loop. So we're going to start at 1 since we already calculated our initial temperature profile, and run to 100. And then I'm just going to go ahead and print out all of these temperatures so we can kind of take a look at them. And so if you take a look at this, kind of scroll up to the top, you can see how the heat is slowly diffusing in. So here, the temperatures are raising. The next increment, they're raising even more. And the next increment, they're raising even more. So to kind of get a look at this, I say we just go ahead and graph it instead of printing them out. And so I'm going to go ahead and up here, make our subplot. And then we'll go ahead and graph our initial temperature profile. So before we go ahead and do that, we need to get a set of x values. And so I'm just going to set x equal to np arrange n. So this will give us an array from 0 to 19 to graph our to graph our temperature profile. So x will be equal to x, our y value is t, and then to make sure it's a smooth curve, I'm going to set the mode equal to lines. And so there is our initial temperature profile. So now coming down here, we just have to add the scatter, add each temperature profile as it's calculated. So again, x will equal to x, y will be equal to our temperature, and to make sure it's nice and smooth, we'll give mode lines. And then to make sure it shows up, we can do figure 1 dot update layout, and I'll just go ahead and set the width to 800, the height to 600, and I'm going to change the template to dark so it kind of matches the theme of my collaboratory. And so there are our temperature profiles. Right now we're graphing 100 different lines, so it's pretty messy. And to clean this up, I'm going to go ahead and make sure that we only graph every 10, because that'll help us see it a little bit better. So to do that, we just need to add in an if statement. And so if I, and we take the modulus of I, so I mod 10, and if that's equal to 0, so every time I is evenly divisible by 10, it'll be equal to 0. We want to graph, make sure this is indented. And then I'm just going to go ahead and run these other blocks to make sure it resets. And there we have our temperature profile. So we can actually go a little further and insert the names using an F string. And if we put our variable in a bracket, it'll actually display the variable instead of just I. So we can do the same thing over here, give it a name. And this is at time 0. So go ahead and run all of our blocks again, make sure the code resets. And here we have our temperature profiles of our bar over time.